Hi, everyone. Thank you for coming to this talk. I'm Anna. I work thank you for the introduction. As I was introduced, I work at Isovalent as a software engineer. I'm focused on observability. I work on observability tooling day to day, tooling that is built on top of eBPF. And today I will talk about eBPF. So what is eBPF? It's not something new. It's been there for a while. It got some traction already, and many, if not all of us, use eBPF in some way day to day, even without realizing it. But it's also a technology that most of us use indirectly. So there is a lot of confusion about what it is, how it's actually used, especially in observability context, and this is something I will try to clarify today in this talk. So, introduction to eBPF in 5 slides. Let's start with that. eBPF is a technology that makes the Linux kernel programmable. The commonly used comparison is that eBPF is to the Linux kernel, same thing as JavaScript is to browser. So it allows us to execute code inside Linux kernel. We are in the observability track. So I will show some of the eBPF features that make it especially useful technology for observability. So the eBPF allows us to run custom code in the kernel. And normally, when we write applications, we are running them in user space. They are running there happily, but whenever the application needs to touch the underlying infrastructure, it needs to reach out to Linux kernel via system calls. It can't do this on its own. And that happens a lot. Whenever the application needs to read a file, make a network call, or allocate memory even, it needs to reach out to Linux kernel. Now, with eBPF, we have eBPF programs that can run in Linux kernel and are attached to certain events. I will describe what kind of events this can be in the moment, but eBPF programs are attached to events and executed every time these events happen in the Linux kernel, no matter what application and what application triggered that. So eBPF programs are attached to events, and there are many, many different kinds of them. The few ones that are most relevant for observability, I would say, are listed here. So there are kprobes and kret probes, kernel probes, which allow us to attach events to kernel functions defined in the Linux kernel. There are uprobes and uret probes that are their counterparts for user space functions. The red version of these attachment points are executed on return when the function returns, and kprobes and uprobes when the function executes, when it starts. There are perf events. Perf events are very interesting for observability. Perf is a profiler, a tool built into the Linux kernel that collects monitoring system information. It's built into the Linux kernel, and it's often used by Linux administrators to observe what is going on the system level in the operating system. Now, perf produces events, and we can attach eBPF programs to them. So that allows us to enrich these events, to process them in the Linux kernel, and produce some richer and more useful observability data for user. There are also trace points and user space trace points, USDTs. These two are very similar to kprobes and uprobes in the terms that they allow us to attach to certain functions, but these are statically defined trace points, or USDTs, user space trace points. So they are statically defined, meaning that they are limited. They don't allow us to attach to absolutely everything, but they are also considered more more stable than raw kprobes or uprobes. eBPF is commonly thought of as something that allows you to attach to syscalls. This is one use case that you can see on this example program here on the slide, but that's just one pretty simple example of what can be done. eBPF allows us to attach to many different points. And eBPF code is written in C. As you can see here, it's a pretty simple program written, example program written in C. These days, I think it can also be written in Rust, but yeah, usually it's C. Now, most applications that we write are not pure functions. They have some state, a database, a cache, something. This is when computer programs become really interesting and useful, when they have a way to store some trace, some state. And eBPF programs are no different. They also become really interesting when they can store state. In BPF world, it's done with BPF maps. There are many different kinds of BPF maps, but they are basically key value stores. There are key value stores stored in the Linux kernel memory. Well, some of the most popular ones are, for example, hash table or perfring buffers, and they are needed for observability specifically. They are needed for very obvious thing. You want to report data somehow to the user, right? The user wants to observe things that are being tracked by eBPF programs. So to report things back to the user, you write them to BPF map so that they allow you to communicate between kernel space and user space. Another thing is that BPF maps allow us to communicate between different eBPF programs. For example, when the function starts and when the function returns, we can trigger different programs that we can coordinate the logic with BPF map, or we can also correlate things that are happening between two completely different events in the Linux kernel, so that allows us to execute some more complex logic, observe more complex things inside the Linux kernel. All right. And last part of the intro to eBPF is, this is not exactly a new idea. Making Linux kernel programmable, somehow customizable, was possible with kernel modules for a while. The problem with that is that, well, kernel modules require you to, it's basically like programming Linux kernel. You need to compile kernel with them. They allow you to do anything, execute anything in the Linux kernel. People are usually very cautious about executing them for a good reason, because if there is a bug in a kernel module, then it will cause kernel to crash, so the whole machine to crash. With eBPF programs, this is not a concern, because eBPF programs go through a verifier. So a verifier is a tool that checks if a program is safe to run, meaning that it doesn't go to an infinite loop, it doesn't access memory, it shouldn't access things like that. When the program goes through verifier, it's accepted, only then it's actually loaded and attached to certain event. So that means that you don't have to recompile the whole kernel to run these programs, and you can be reasonably sure that they won't crash your kernel. So it's important for observability tooling. You generally would like to run it, like just load it, for example, as some deployment in Kubernetes. You don't want it to be something that only Linux administrators can run. All right. So I touched a bit around why eBPF is useful in observability, let's dive a little bit more into that. So these days we are running things in Kubernetes. In Kubernetes, we have many applications running on same host. And they are rescheduled. They are started by Kubernetes all the time. From the application perspective, we generally don't care which host the application runs on. But what is true for Kubernetes and for every other environment is that there's always only one kernel per host. There is only one kernel, and all these applications reach out to this one kernel to do various operations, like network calls, file operations, everything, basically everything that touches any kind of underlying resources. Now, this kernel can run eBPF program that see everything that is happening in the user space, so see all the applications running on the host. It doesn't care what applications are running there, because it's attached to a kernel event. So it doesn't matter for eBPF program what user space application really triggered that event. And because it's running inside Linux kernel, it doesn't have to do all these hops between kernel and user space to do useful things. So normally, the applications are doing tons of these system calls. eBPF programs can reduce this number because we can execute some logic, we can process some data inside Linux kernel and just report it to the user space. We don't need to go back and forth all the time. This all happens without any changes to code or configuration in the user space. And this is something that is basically holy grail of observability, something very desirable by many people. Everybody would like to have great visibility into what's going on in their applications, but usually that requires instrumentation. Instrumentation is often hard, difficult. It often takes a lot of time. It's often difficult to organize if we have multiple teams working together on same things. It's an additional cost that we have to maintain. So having visibility, some visibility without any instrumentation is always great. It's something that it's often not sufficient. I will touch on that later, but it's something that often speeds up adoption of various observability tools, and it often gives this initial visibility of what is going on if the application has no visibility at all. Okay, let's move on to some eBPF observability tools. So usually, most of us wouldn't write eBPF code ourselves, I would guess. I generally don't, despite of working, I work on tooling that uses it indirectly. But generally, we would use eBPF through tools that have some eBPF code in them. In observability space, there are many of them. Let's take a look at some of them. So this is the first thing I wanted to talk about. This is a diagram that I think it's probably is shown in every second talk about eBPF. Author of this diagram is Brendan Gregg, and it shows BCC, BPF compiler collection, which is a collection of various small tools that give us visibility into tons of different things that are happening in the operating system. They're also called sometimes libBPF tools. libBPF is a C library that takes care of compiling and loading eBPF programs. So there are many of these small tools for observing memory, disk, runtimes, libraries, many different system-level things. And this is a screenshot of the eBPF tools repository. Each of these tools is just 3 or 4 small files. They are, by the way, they are great examples if you want to learn eBPF or write eBPF code yourselves, because these are small, self-contained tools. They are really great examples. This is just a small part of the whole list, as you saw. There are many of these tools, but they are all there and they are pretty small. Now, there is this project from Cloudflare called eBPF Exporter, and their README says it's BCC tools as Prometheus metrics. And I think it says it all, probably. What eBPF Exporter does is it transforms BCC tools, data produced by BCC tools, into Prometheus metrics. When you write a configuration file, like here you can see an example, configure what tools you want to use and what metrics you want to see, and it produces BPF code for tracking these tools. Now, second thing I wanted to talk about is something I work on at Isovalent. Isovalent is mostly known from the main product, Cilium, which uses eBPF for networking. So there are a few different use cases for eBPF. I'm talking mostly about observability, but networking is one big thing. Cilium is Kubernetes networking plugin, very rich in features networking plugin. And it implements networking with eBPF. Now, it's not a talk about networking, we talk about observability. So Cilium has this visibility layer called Hubble. Hubble is processing data produced by eBPF injected by Cilium and exposing them to the user. If we are implementing networking with eBPF, then, well, of course, in these eBPF programs, we are forwarding packets and so on. But if we are doing that, then we can as well write this data back to the user and report it in some observability tool that is integrated with the whole ecosystem. So this is where Hubble comes. Hubble provides CLI for observing network flows. So here you can see an example of CLI command that allows you to observe these individual network flows with all kinds of filters that you can imagine, including like Kubernetes metadata, labels and stuff like that. Hubble also exposes Prometheus metrics, and we have a Hubble Grafana plugin. So in observability space, there are so many different platforms these days. I think many of you probably can relate to these problems when you have tons of different tools and tons of different tabs in opening browser and trying to make sense of them all. So I think it's a very common challenge that we are trying to put all this data somehow together to have this data living in different places, coming from different sources, but available only in one browser type so that we can actually use it easily when troubleshooting. And this is when things like metrics produced from eBPF events or Hubble Grafana plugins are really useful. They allow us to put all this data together and correlate them. So we have Hubble Grafana plugin that allows to visualize individual network flows that are happening, that are tracked by Hubble, and also visualize Prometheus metrics generated from these flows. Okay, another tool I wanted to talk about is Tetragon. Tetragon is a tool focused on security, so observability from security perspective mostly. Here we see an example of configuration. Tetragon is configured, it's used in Kubernetes, dedicated for Kubernetes, and it's configured via Kubernetes custom resources, tracing policies, which where in this configuration you can see that we define K-probes. We define which K-probes we want to track with Tetragon. In that case, it's fd install. It's kernel function that is responsible for various file operations. And we see that we define also arguments, what arguments have to be passed so that it's called. So in that case, we basically want to see file operations that happen to files under etc directory. This might seem like not very simple configuration. We are going pretty low level details here. However, this is something that is often necessary with eBPF. The amount of data we can track with eBPF is so huge that this kind of configuration might be necessary to just prevent tracking absolutely everything that would absolutely overload our systems. And here we have an example of Tetragon output. We can see these individual events that happened to a file, how it's opened, closed, and how we write to. In this case, I believe we are observing when somebody changed a password. Okay, so that would be it about Tetragon. We were talking so far about observing low-level, very low-level system events, but in the observability space, there are certain user-level areas that are gaining a lot of traction now, and one of them is continuous profiling. Continuous profiling is gaining popularity in observability space as kind of new signal. There are a few continuous profilers available these days, Parka, Pixie, and Pyroscope. Here we can see a screenshot from Parka, the icicle graph from Parka continuous profiler. And let's now take a look at some eBPF code. Again, this is Parka's code. This is Parka's eBPF code. It's very truncated for the purpose of showing it on slides, and it might be not very readable for you all here, so let's put some arrows on it. So what Parka does is, Parka defines this profile CPU function. This function takes BPF perf event data structure. So this is the context argument that every BPF program gets. What context argument is passed depends on where we attach the eBPF program, so depends on the attachment point. This program is attached to perf event, and it receives this structure defined in the Linux kernel. Now, there is some reading from BPF map, there is some writing to a BPF map. Writing is defined in some helper function. The point being that this BPF program, what it basically does, it stores parts of the profile in the BPF map, and by attaching to perf events, it's able to construct the whole profile for the application and do that continuously. Here's the user space code for Parka. So BPF programs have to be loaded into the kernel somehow. They are not loaded when we are starting Linux kernel. They are not compiled with Linux kernel. They are loaded by user space programs. This is Parka's user space program in Go. And here, relevant things are that it is it's attaching function to perf event using eBPF Go. eBPF Go is one Go library for handling these BPF programs in the user space. And the profile CPU function is the name of the function we saw here. So it's basically attaching this function to perf events. Now, another thing that is a kind of hot topic in the observability space is distributed tracing. This is a screenshot of trace in Jaeger. We can see here that it's some trace of some application. We can see that I think it's MySQL that is the longest bar here. It's probably bottleneck. We can see this stairs pattern. These are calls to Redis that maybe could be parallelized. So this is pretty useful trace that tells us a lot what the application is doing and what are bottlenecks there. To get that, we have to, such trace for the whole application, we have to propagate trace headers. And this is often difficult because, well, if we have applications written in different languages, then we can be using different frameworks. We need to do that separately for each of the tools we are using, the languages and the frameworks. What if we could do that automatically? There are automatic trace context propagators for some of the languages. For many languages, it was difficult because, especially for compiled languages, it was difficult because in compiled a version of the program, we just can't see this, we can't easily inject this propagation. It's possible with eBPF. So there is a project under OpenTelemetry umbrella for Go auto instrumentation using eBPF. This is eBPF code. Again, let's put some arrows on it. These eBPF programs are attached to uprobes. Uprobes for Go gRPC functions. And we have two eBPF programs attached here for invoke and invoke returns user space functions. And what is going on here? This code is, again, very, very heavily truncated to fit it on the slide. But eBPF code is reading trace headers and writing them to eBPF map and propagating them between applications in that way. And again, user space code that is injecting tracing auto instrumentation. It uses different library. It's Cilium eBPF library, also a Go library that allows you to load eBPF programs, and it attaches them to uprobes, as you can see. OK, so can we actually use eBPF for everything, for instrumenting, for not instrumenting everything? Well, the problem with eBPF is that it doesn't really have business context. What happens in the applications is that we see that Tom adds milk to cart. Some user does something. What happens in eBPF, what we can see in eBPF is file operations, socket operations, things like that. Linux kernel does see everything, but doesn't really understand what is happening. Observability with eBPF is challenging. Because of this reason, it's really difficult to give eBPF all this business context. Sometimes often it's impossible, and it's just completely impractical. It's still young. It's still very young. Areas like continuous profiling and tracing auto instrumentation are super promising. I'm really excited to see that, but it's still very young. And the data volume can be absurd. I mean, in observability space, we are often struggling with the scale, with number of metrics, things like that. With eBPF, that's completely different level. Like the data that we can get from various tools that are just observing every single event is completely absurd. So what is possible today? With eBPF, we can get system metrics with absolutely no instrumentation, no changes, that's absolutely possible today. We can get that with pretty simple configuration of the eBPF tools. We have network and security visibility. There are tools for that, and they are getting pretty good integrations into whole observability ecosystem. So they are not just isolated niche tools, but we can actually use them and give them to wider audience. There is continuous profiling. There are a few of them, but it is there. It is gaining popularity. And there are attempts at distributed tracing auto-instrumentation. It's still very early. I'm super excited to see how this space will develop, but it is there already in some form. Thank you very much. I think I'm a minute over time. If you want to learn more, at Isovalent, my amazing colleagues, Liz and Natalia, wrote books about eBPF, and it's because we are a sponsor here, we brought some of these books, so you can get a copy of Learning eBPF, I believe today evening. Liz will be signing them, and tomorrow at lunchtime, Natalia will be signing a book about Tetragon, security observability with eBPF. You can also download them for free from the Isovalent website. You can download PDFs there. Thank you very much.